Today we will talk about an alternative definition of the notion of modules. So we've seen the following. We need a ring R, and what is a module? So M is suppose an R module. Then what does that mean? It means that M is an abelian group and it's got a scalar multiplication by scalars coming from the ring R. Okay. So now let's rephrase the axioms that scalar multiplication satisfies in a more compact form. Okay, that's going to be our goal for this lecture. So let's first make some observations that if M is an abelian group, so recall M plus is an abelian group. Now let me define something called end of M. So where end stands for endomorphisms, by which we mean homomorphisms from the group M to itself. So it's all F from M to M such that F is a group homomorphism. Okay, so this is something that I can consider. Given an abelian group, I can look at the set of all homomorphisms from the group to itself. Now the key observation is that this set N M actually has some additional structure. So what can I do? N M itself has an addition operation. So it has an addition. What is the definition of addition? If I take two homomorphisms F and G, then I can add them as follows. This is called pointwise addition. I can look at f of x plus g of x. This is for all x in M, and this would of course be also a homomorphism, as you can check easily. The second important observation is that I have a composition of maps. So I can look at f composition g of x, which is defined to be f of g of x. This is for all x in M. Now f composition g is also a homomorphism. So f plus g and f composition g are in fact both elements of end M. In other words, they are both homomorphisms from M to M. Okay, so it's an easy verification which I will leave you to do. So what does this mean? It means that the set end M actually has two operations, an addition and well a sort of multiplication, which is composition here. And the key fact here, key observation, is that with respect to these operations, the set of all homomorphisms under pointwise addition and composition forms a ring. Okay, so this is a ring. Now what does that entail? You need to check all the axioms of a ring. So addition of course is commutative, is easy to check. Composition of maps is an associative operation, as you have no doubt seen before. And what else is required? The identity map. Okay, so we need to show well distributivity as well. So let's just check those two axioms. So let's check the distributivity axiom, that multiplication distributes over addition. So that means if I look at f composition g plus h, then that's got to give me f composition g plus f composition h. So let's compute what's this homomorphism on x. This is by definition f of g of x plus h of x. But the key thing here is that f is a homomorphism. Therefore f of a sum of two things is just going to be f of the first guy plus f of the second guy. Okay, so this is because f is a homomorphism. So that's the first distributivity axiom, because well what's on the right hand side is exactly f composition g plus f composition h. So it's this guy evaluated at x by definition. Okay, so that's the first distributivity axioms. You can check the other one similarly. If I take f plus g of x, f plus g composition h, this is in fact simpler. This is just directly by definition g composition h. Okay, now this is easy. And lastly, let's check the identity axiom. So I need to have an identity for the multiplication, and of course it's clear what the identity should be. It's just the identity operator on M. Okay, so let's look at IM, which is the identity operator. Now IM is, well, it satisfies this property. If you compose the identity operator in either direction, of course it gives you back the original function. Okay, so IM is the identity map. It sends x to x for all x in M. okay, and that's a homomorphism. So the key property here again is that the identity is in fact a group homomorphism. Okay, so what that completes is the proof that the set of endomorphisms forms a ring under these two operations, the pointwise addition and the composition of maps. Okay, now let's try to let's try to see what we can get out of this new structure. So suppose M is if M is an R module, okay, that's given. So what does that mean? In addition to my additive group structure on M, I am given this map from R cross M to M, right? That's the scalar multiplication. So what do I have? I have a map from R cross M to M, alpha comma x, mapping to what we'll call alpha dot x, the scalar multiplication of x by alpha. Now this map, let's try and encode it in the following manner. So it's the very same information but written slightly differently. So let's do the following. Let's fix the alpha. Okay, so I fix a certain scalar in the ring, and when I do that, what it defines for me is a map from M to M. Okay, what map is this? It takes each element of M to alpha dot x. So alpha is fixed, so this map of course is dependent on alpha, but this is the scalar multiplication by alpha map. Okay, so it's a map from M to M. So let's check what are its properties. So observe axioms. So remember we have axioms for the scalar multiplication. So axiom number 1 of modules says that if I take the scalar multiple of x plus y, that's alpha dot x plus alpha dot y. Okay, in other words, if I look at phi alpha, this map, scalar multiplication map on x plus y, it just gives me phi alpha of x plus phi alpha of y. In other words, phi alpha is a group homomorphism. So this belongs to this set end M that we just constructed. Okay, so phi alpha belongs to end M for all alpha in R. So that's the first observation that we are making. Now the second observation is, so the first axiom is in some sense taken care of. The first axiom just says that this map phi alpha is a group homomorphism. Now let's encode the remaining three axioms. So let's look at axiom number 2. So it said that, so this is axiom 2 of modules, said that if I take alpha plus beta and scalar multiplied by x, the answer is same as alpha x plus beta x. Okay, now in terms of this map phi alpha, this is what it says. If I take the map phi alpha, which is scalar multiplication by alpha, take the map phi beta, and I construct their sum. Okay, this is now the sum in the endomorphism ring of M. Remember, this just means it's the pointwise addition. So consider phi alpha plus consider phi of alpha plus beta, that's the left hand side, scalar multiplication by alpha plus beta of x is the same as scalar multiplication by alpha plus the scalar multiplication by beta. In other words, it's the pointwise sum of these two endomorphisms. Okay, and this is true for all x. So another way of restating axiom 2 is to say that this map phi alpha plus beta is the sum of these two maps, phi alpha plus phi beta. Okay, it's the pointwise sum. Okay, now axiom 3 similarly, you can already start seeing where this is going. The scalar multiplication by the product phi alpha beta by the product alpha beta, this by definition is alpha beta acting on x, but that, remember, is the same as alpha acting on beta acting on x, but that just means it's phi alpha composed with phi beta of x. So this axiom 3 can be restated as follows: phi of alpha beta is just phi alpha composition phi beta. Okay, and axiom 4 finally just says that the identity map, the identity element, the scalar multiplication by the identity just gives me the identity map. Okay, this just says 1 multiplied by x is x. So what I have done is to recast the 4 axioms in terms of this map phi alphas that I defined. Okay, now all of this can now further be recast as follows. Consider the map. So let me now consider the following map. So remember, I had fixed alpha so far. Now let me let alpha also vary. In other words, let me look at the map. So let us call this phi now. It takes each alpha to this scalar multiplication by alpha map. Okay. So consider this map alpha going to phi alpha. Now what we have shown is that axioms, so the foregoing discussion, axiom 1 says that phi alpha is in the endomorphism, axioms 2, 3 and 4 say exactly that phi is a ring homomorphism. Why is that? Well, because the operation of addition in this ring end M is exactly this pointwise addition. The operation of multiplication in this ring is exactly this operation of composition, and the identity in this ring is exactly this map identity M. Okay. So these three axioms here just say that this map phi is actually a ring homomorphism. Okay. So and as you can easily check, you can sort of go back the other way around as well. In other words, if you are given a ring homomorphism, you can from that construct a module in the usual sense of the word. So here's the definition 2 of modules. So let me give you the second definition of modules. You can simply say an R module, or this is all, so I am always talking about left modules. So like I said last time, if I don't say anything, I always mean left. An R module M is an abelian group, M plus, together with a map, together with a homomorphism of rings, let's call it phi, from the ring R to the ring end M. This is another way of defining a module. Okay. So what we have just seen is that if you use the first definition of modules, then from that you can construct this map phi. Okay. The map phi is just each alpha going to the scalar multiplication by alpha map. Conversely, if I give you a module according to definition 2, it satisfies definition 2, then you can show that it satisfies definition 1 as well. Okay. In other words, given this map phi, given such a map phi, you can construct the scalar multiplication map or M to M as follows. If I give you an alpha and an x, since I sort of know what my phi should be doing, so I'll just do the following. I take phi, I evaluate it on alpha, so that gives me sort of the scalar multiplication map. So it's an element of end M, and I evaluate it on x. Okay. So I can construct my scalar multiplication map in this way. Okay. So I'm going to leave the details for you to check. Check that a module by definition 1 is also a module by definition 2. Okay. In other words, definitions 1 and 2 are equivalent. Okay. Is also a module by definition 2 and vice versa. These two definitions are equivalent. Okay. And the second definition is sometimes convenient. It's important to know this way of thinking as well. It's definitely far more compact, right? It sort of encapsulates all the axioms into one single statement that you should have a map from R to end M, which is a ring homomorphism. Okay. Now let's look at some of our previous examples of modules and see how they match up in this point of view. So let's do one particular example. Let's look at the case of Z modules. Example, suppose my ring R is Z, the ring of integers, then recall that a Z module by definition 1, we more or less figured out that there is only one possible scalar multiplication that you can define on a module, and that turns out to be just the the map which sends n comma x to x plus x plus x n times. Okay. So look back on the lecture, one of the previous lectures, but now I just want to see what I will get if I apply definition 2. Okay. So let's take R equals Z, and let me say I want to look at M, which is a module over Z, according to my second definition. Okay, so by say the second definition, what does that mean? Suppose M is a Z module according to my second definition, i.e. that just means, what am I given? We are given a map from, so we are given a ring homomorphism from the ring R to the ring of endomorphisms of M. Okay, and R here is just Z, it's just the abelian group Z. Okay, now this is sort of the scalar multiplication map, right? It keeps track of the scalar multiplication, i.e. we are given a ring homomorphism like this. Now observe, last time we figured out that according to definition 1, there is just one module structure, Z module structure you can give on an abelian group. You can't really make it a Z module in any other way. Okay. Now what that translates to here is that if you're trying to construct a ring homomorphism from the ring Z to the ring end M, well, then there is actually a unique ring homomorphism. Okay. You cannot find two different ring homomorphisms from the ring Z to the ring end M. Okay. So claim or little fact, in fact not just to the ring end M, if S is any ring, whatsoever, in particular I can take S to be end M, there always exists a unique ring homomorphism from Z to S. Okay, so let's prove this. Well, the ring homomorphism from Z, suppose I have a ring homomorphism F. So suppose if F is a ring homomorphism, so observe that it has to satisfy many important properties. In particular, by definition, the ring homomorphism sends identity to identity. Okay, so the identity element, so let me call this multiplicative identity of S as 1 sub S. So the integer 1 has to map to 1 sub S. Okay, that's one of the properties that a homomorphism should satisfy. But as we have seen before, I mean, this is sort of the calculation we did earlier. If you know what 1 maps to, then more or less everything is fixed. Okay, why? Because any other number n is just 1 plus 1 plus 1 so many times. Okay, so this is just, I take, suppose n is positive, then I can write n as 1 plus 1 plus 1 so many times, which means that this homomorphism F must map f of n to f of 1 plus f of 1 plus f of 1 so many times. In other words, it has to map it to 1s plus 1s plus 1s added n times. Okay, f of n has to be this, there is no other choice for n positive. Okay, so similarly, if n is negative, now you just have to do the same sort of calculation we did before. F of 0 is 0 and therefore f of minus n is minus n. Okay, so when n is negative, show that. So let me leave this little step for you. If n is negative, show that f of n is just going to be minus of 1s plus 1s plus 1s n times. This is modulus of n times. Okay, and if n is 0, then of course f of 0 is 0. So that's also one of the first things that one should have done. If n is 0, then f has to map it to the additive identity of S. Okay, so if you're trying to construct a ring homomorphism from the ring Z to any other ring, in some sense you have no choice, everything is forced on you. Okay, and that's really a reflection of the fact that there are, if I give you an abelian group, I can't really make it into a Z module in any other way. There is just one way of making it into a Z module. So that's sort of very clear from this second definition, from this way of thinking about it. Okay, now let's look at left versus right modules. So remember the axioms I had mentioned for modules. I also included axiom 3 dash. If it were to be a right module, we said that it should satisfy axiom 3 dash, which says that phi, I mean the alpha, so recall, so suppose if M is a right, if M is a right module, if M is a right R module, then the scalar multiplication map alpha x mapping to alpha dot x satisfies axioms 1, 2, 4, but instead of 3 it satisfies axiom 3 dash, and if you recall what this was, this says the product alpha beta on x should be beta acting on alpha acting on x. Okay, so the question is, what does it become from the second definition point of view? Okay, so let me just state it. It should be more or less clear. Equivalent definition is the following, analogous to the definition we gave for left modules. So M is a right, what is a right module? A right module is an abelian group together with right module M is an abelian group it's called the operation as plus together with well, what are we given? We are given a map from R to the set of all group homomorphisms of M. It's called this map phi as before. Now the property that phi has to satisfy is the following, that this is what's called a ring, not a homomorphism, but what's sometimes called an anti-homomorphism. Phi from R to end M. In other words, phi is, well, it is almost a homomorphism. Phi of alpha plus beta is phi alpha plus phi beta. Phi of 1 is 1. In this case, the identity. These two are okay, but phi of alpha beta is phi beta phi alpha, so it just goes in reverse. Okay, so this is really what the axiom 3 dash now becomes, that phi of alpha beta should be phi beta phi alpha. Okay, so what this again means is that right modules are almost the same as left modules. Instead of being given a homomorphism to end M, you are given a anti-homomorphism. You are given a map which switches the order of these two numbers, of those two elements. Okay, so this switching of order of elements can sort of be again formulated as a new notion. So this is what's called the opposite of a ring. So let R be a ring, then the ring, we define the ring R opposite. So this is called the opposite ring of R. So what's the opposite ring? Well, it's to say that this is a ring, I must tell you what the operations are. The ring R op is defined via the following. R op is the same as R as a set. Okay, the underlying elements are the same as the elements before. What is the addition operation in this ring? So let me now put a circle around it. So this is a new operation. The new addition operation is the same as the old addition operation. The new multiplication operation is the same as the old multiplication operation, but carried out in reverse. Okay, so this is the thing, and the identity element will turn out to be the same as the identity element of R. Okay, so this is the new identity is same as the old identity. So check that this makes R op into a ring. Okay, so here's an exercise. If I am given a ring, I can consider or construct the opposite ring. So exercise prove that R op is in fact a ring. Okay, now observe some obvious facts here, that if I take a ring R, I construct its opposite ring and I construct the opposite of the opposite ring, then it's just isomorphic to the original ring. Okay, why? Because the opposite ring involves interchanging the order, and you interchange the order twice. So that's the first property. Property 2 is that if the ring is commutative, then this opposite ring business is really not required. The opposite of a ring is the same or is isomorphic to the original ring if R is commutative. Okay, so for commutative rings, the opposite is the same or isomorphic to the original. But the converse is not necessarily true. You can have, if a ring is non-commutative, it can still be isomorphic to its opposite. Okay, and a standard example of that is if I take the ring to be the ring of, so this is an example, if I take the ring of n cross n matrices, then so what does the opposite ring mean? It means if I give you two matrices A and B, their new product is defined to be BA instead of AB. Okay, observe that from the ring to its opposite, I can actually define a very natural, nice map. This is a matrix going to its transpose. Okay, and this map psi, observe the property of transpose is that if I take AB and transpose it, it's the same as B transpose A transpose, right? It switches the transpose operation switches the order. What does this mean? This just says that this map psi is in fact a homomorphism of rings. I mean, you have to check it also satisfies the additivity and so on. So let me leave you to check this, that psi is in fact not just a homomorphism, it's actually a bijective homomorphism. So it's an isomorphism of these two rings. Okay, so the matrix ring is in fact isomorphic to its opposite ring by means of this nice map, which is the transpose. Okay, so what's the reason for wanting to construct the opposite of a ring? So observe again that a right R module, so here's the final important fact, is the same as, well, or it becomes a left R op module. Okay, why is this? Because observe, if I had a right module, so if M were a right, so it's a right R module. If M is a right R module, which means, let's look only at that axiom 3, which is the key difference. If I take the product of alpha beta and then act it on X, then the answer is just beta acting on alpha acting on X. Right? So that's the third, that's axiom 3 prime. This is what right module satisfy. But this product alpha beta that I have here, this is the product in the ring R. If I think of alpha and beta as being elements of the ring R op now, I mean R and R op are really the same underlying set. So think of the elements alpha and beta as coming from the opposite ring. Then observe that this product alpha beta that occurs here is actually in the opposite ring. It's the product of beta with alpha. Okay, so this is the product of the opposite ring. Product operation R op. Okay, so what does that mean? It means that if I rewrite this identity, this equation or axiom star can be rewritten as follows: take beta and multiply it with alpha, but do the multiplication in the opposite ring. So this is the R op wala multiplication, then multiply it with X, then the answer is the same as the right hand side, which is beta acting on alpha acting on X. Okay, and now this axiom, as you can see, is axiom 3, right? This is now in the correct order. So remember, this holds for all alpha beta in the ring R. So I can, like I said, R and R op are the same set, and for all X in the module M. Okay, so this new identity just means that if I consider M as an R op module rather than as an R module, then it becomes a left module over R op. Okay, so this is the key statement here. Right modules over the ring are the same as left modules over the opposite ring, and so in some sense whatever we prove for left modules will automatically hold for right modules with sort of the appropriate modification in notation and so on. Okay, so we will usually only talk about left modules for this reason, that you can quickly convert any result about left modules right modules by just looking at this opposite ring construction. But that is not to say that right modules are not important. In fact, they will turn out to be extremely important in many things that come up. In fact, what's also very important is modules which have both, what are called bimodules, modules which are both left and right modules and so on. Okay, so it's equally important to keep thinking about left and right modules. Okay, we'll stop.